Hi everyone, my name is Shahar Samocha, and in this talk I'm going to present a joint work with Gil Cohen, my advisor, about a new notion of tree codes which we call palette alternating tree codes. Our motivation for doing so is devising a deterministic interactive coding scheme that achieves capacity. But before I delve into more details, let me first define what interactive coding schemes are. Okay, so in this setting, we have two parties, represented by Alice and Bob, where each of them holds an n-bit string, and they want to jointly compute a function of their inputs. We only care about the communicational complexity of the protocol, namely the number of bits that have been sent across the channel, rather than any computational aspects. In our work, we focused on alternating protocols, meaning that at each round, only one bit is sent, where at the odd rounds, Alice sends one bit to Bob, and at the even rounds, Bob sends one bit to Alice. It's good to keep in mind that protocol pi consists of r rounds, where r is much smaller than n, and so it makes sense to encode the entire conversation rather than encoding one of the inputs and send it. Assume now that the channel is noisy. A noisy channel could be modeled in various ways, but our focus is on the bit flip model with adversarial errors, meaning that there exists an adversary who can corrupt up to epsilon fraction of the messages that sends across the channel. Notice that this model assumes nothing on the error location pattern. An interactive coding scheme is an algorithm that, given a protocol, outputs a new protocol which is resilient to this fraction of errors. We define the rate of the scheme to be the number of bits that sends in protocol pi divided by the number of bits that sends in protocol c of pi, taking minimum over all the protocols. Notice that it's completely non-trivial that such an algorithm with non-vanishing distance is even exist. The channel capacity is defined to be the maximal rate that can be achieved over a channel with epsilon fraction of errors. In a seminal paper, Shannon showed that the channel capacity in the single message case is 1 minus the entropy of epsilon up to constant factors. In the early 90s, Schulman introduced the notion of interactive coding schemes and showed the existence of such a scheme with constant rates. Since then, there has been a variety of works regarding this subject who studied the error rate trade-off, which are all well explained in Gales' excellent survey. Here we only choose to mention Cole and Raz paper, which state that the channel capacity in the interactive setting is bounded from above by 1 minus the square root of entropy of epsilon, which is a tighter bound than the one that Shannon did for the single message case. A little bit afterwards, Gales, Hopler, Cole, Ronsby, and Wittgerson show the existence of such deterministic interactive coding scheme with the same rate, namely 1 minus the square root of the entropy of epsilon. In our work, we also show the existence of such a scheme, but using different ideas that we believe are more amendable for their randomization. In a sequence of works, Schulman defined combinatorial objects named tree codes. This tree code serves as a key ingredient for almost every deterministic interactive coding scheme that we've seen so far. Let us now define it using an example. So consider a tree as shown in this picture, namely binary and complete. Actually, we are considering every complete binary trees of any depth, but for simplicity, let us assume that this tree is infinite. Now, an edge coloring over some set of colors is called a tree code with distance delta if the following property holds. For every two vertices of the same depth, the relative Hamming distance of the path between their least common ancestor to them is at least delta. Let's look on an example to understand. Consider vertices u and v in the graph. Notice that their least common ancestor here is w, which happens to be here the root of the tree. Now the path between w and v is colored by orange, blue, and orange. And the path from w to u is colored by red, green, and orange. Note that only the last edge is colored by the same color, and so the relative Hamming distance between U and V is 2/3. The distance of the tree code is determined by taking minimum over all the pairs of vertices of the same depth. An insight is that if we have a tree code with distance strictly larger than 0, we can't have two edges that go out of the same vertex that have the same color. Look at this example on vertices U and V. Notice that their least common ancestor is W. And so the only edge on the path between W and V and W to U is the two edges that are colored with blue. And so the relative Hamming distance is 0 between U and V. And so does the distance of the tree code. And so if we have a tree code with distance which is strictly larger than 0, we can't have any two edges that go out of the same vertex with the same color. As mentioned before, a result by Schulman is that there exists a binary tree code with constant distance and constant number of colors. But as we will see later on in this talk, the number of colors used for constructing the tree code affects immediately the rate of the interactive coding scheme that uses it. So we asked ourselves, what is the least number of colors needed for constructing a non-vanishing distance tree code? Where non-vanishing means that the distance is not going to 0 while the depth of the tree is going to infinity. Clearly the 2 colors is not enough, but what about 3? So here's a challenge. Try to prove that every edge coloring that uses only 3 colors cannot construct a non-vanishing distance tree code. Our next step was to prove that also 4 colors are not enough. But on our way to try to prove it, we actually realized that we can prove that there exists a 4-color tree code with distance close to 1/7. We will see the proof concept later on in this talk. The problem is that the rate of the interactive coding scheme, even when fitted with the optimal 4-color tree code, which we prove in our paper to exist, is bounded from above by half. And so it cannot be used in order to construct a deterministic interactive coding scheme which achieves capacity. So we had to come up with some other ideas. We now turn to define what palette alternating tree codes are and what are the differences and benefits of irregular tree codes. So again, consider the infinite complete rooted binary tree. An edge coloring is a palette alternating tree code with distance delta if the same distance property as for regular tree code holds. Namely, for every 2 vertices of the same depth, the relative Hamming distance of the path between their least common ancestor to them is at least delta. The difference from regular tree code is that now we allow the use of different palettes for every layer of the tree. In this example, you can see that for odd layers, we use palettes of size 2, and for the even layers, we use palettes of size 4. Now, although the distance property stayed the same, namely, we want that for every pair of vertices of the same depth, the relative Hamming distance will be at least delta. It seems like the number of colors that this palette alternating tree code uses should be calculated differently in an amortized way. And so in order to encode a palette of size 2, we need 1 bit. And in order to encode a palette of size 4, we need 2 bits. In expectation, we use 1.5 bits. So in some sense, it seems like this palette alternating tree code uses 2.83 colors. In the previous slide, we saw that every non-vanishing distance tree code has to use at least 4 colors. Now recall that we said that the number of colors that the tree code uses affects immediately on the rate of the deterministic interactive coding scheme. So it seems like this palette alternating tree code can become very handy in order to construct the high rate deterministic coding scheme that we wish for. Another property that is worth mentioning is that at first we thought that the two color layers cannot affect the distance at all, as encoding using two colors means nothing. But a closer look made us realize that the way that the two color layers and the four color layers are intervened actually can improve the distance. In our paper, we were able to prove the existence of the palette alternating tree code as shown in the example, namely that uses only palette of two colors for the odd layers and palettes of four colors for the even layers. Actually, we could prove the existence of a much surprising thing. We proved the existence of palette alternating tree code, where at most layers we use a palette of size 2, and only once in a while we had to use a palette of size 4. With this idea, we proved the following theorem, that there exists a palette alternating tree code with distance delta and rate 1 minus the entropy of delta. Observe that this matches the Gilbert-Varshamov bound for standard codes. Recall the upper bound by Cole and Raz for the interactive setting, which state that the channel capacity is bounded from above by 1 minus the square root of entropy of epsilon. This theorem helps us realize that this bound is not caused entirely by the tree code limitations, whereas by the scheme limitations of synchronization together with the tree codes. Okay, so as promised before, we are going to see now the construction of the palette alternating tree code. But before that, we'll see the construction of the four colors tree code, which later helps us understand the construction of the palette alternating tree code. Now, both of these constructions are non-explicit and uses the probabilistic method. The probabilistic method states that we give some distribution over the edge coloring of the complete binary tree and then bound the probability that a bad event happened. Now, if we want a tree code with distance delta, a bad event means that there exist two vertices such that the relative Hamming distance of the path between their least common ancestor to them is strictly less than delta. Now, we stated before that for every tree code with positive distance, we want that every two adjacent edges, meaning that two edges that go out of the same vertex, will have a different color. Now, let's start with some naive attempt and consider the distribution that each edge gets uniform and independent color. Now, if we have a palette of size C and think of C as constant, the probability that two edges will get a different color is 1 minus 1 over C. And so the probability that they get the same color is 1 over C. It means that in expectation, we are expecting to see 1 over C fraction of adjacent edges that have the same color. Now, since we think of this tree as infinite, it means that the probability that none of these edges will get the same color is basically 0. And we cannot expect that this construction will give us a tree code with some distance. So let's see now some better attempts. Okay, so now we'll see Schulman's sophisticated construction, which in our paper we were able to prove actually induces a 4-color tree code. Now let's assume that the tree is of depth n. We define the random variables R1 to Rn to be uniform and independent over the field F4. Recall that the field F4 is the field of 4 elements, which is a field extension of the field F2. Namely, its characteristic is 2. Now, since this is the complete binary tree, each vertex of depth t is equivalent to a t-bit string in the following way. There is a unique path from the root of the tree to every vertex. And so every right turn of this path could be encoded as 1, and every left turn on this path could be encoded as 0. Now, there is only one edge preceding to every vertex. So according to this construction, we define the color of that edge to be sum of I, xi, r with the index t plus 1 minus I, which means that we sum the ri with the equivalent indexes to where xi was equal to 1. Now let's see some example in order to better understand this construction. Now look at the highlighted vertex. Notice that the path from the root to it is a right turn and then a right turn. And so the encode of this path is 1, 1. So the edge that preceding this vertex, namely this one, got the color R1 plus R2. Now look at the new highlighted vertex. Notice that the path from the root to it is a right turn and then a left turn. And so the encode of this path is 1, 0. So according to this construction, the color that this edge got is R2. Now, recall that in the previous attempt, the problem that we had is that we wanted that every two adjacent edges, namely edges that go out of the same vertex, will have a different color, which happened with very low probability. But let's look what happened with this construction. If we look at those two vertices, or these edges, we see that this edge has the color R2, and this edge has the color R1 plus R2. So these edges got the same color if and only if R1 is equal to 0. Actually, the interesting part of it is that for every two edges in the graph, adjacent edges, their color is the same if and only if R1 is equals to 0. Namely, it depends on R1 solely. Now let's see another interesting property of this graph. Look at the red highlighted vertices. Notice that their least common ancestor is this vertex. And so the path from the least common ancestor to the left highlighted vertex is a left turn and then a right turn. And the path from the least common ancestor to the right highlighted vertex is a right turn and then a right turn. And so it seems like they form some kind of shape. Now, Schulman observation is, no matter where you find that shape in the graph, according to this construction, the relative Hamming distance between the highlighted vertices is the same no matter the location in the graph. Let's see what we mean. If we look at those two blue highlighted vertices, their least common ancestor is this vertex. And so it seems like the blue vertices forms the same shape as does the red highlighted vertices. Now let's see the distance property. If we look at the first edge in the graph, in the shape, we see that the left edge got the color 0 and the right edge got the color R1. If we look back to the blue shape, we see that the left edge got the color R2 and the right edge got the color R1 plus R2. Notice that these two edges got the same color if and only if R1 is equals to 0. The same holds in here. These two edges got the same color if and only if R1 is equals to 0. Now, if we look at the second edge, we see that here the edge got the color R1, and here the edge got the color R1 plus R2. Looking back to the blue shape, we see that this edge got the color R1 plus R3, and this edge got the color R1 plus R2 plus R3, meaning that these two edges are equal if and only if R2 is equals to 0. And same here. These two edges got the same color if and only if R2 is equals to 0. Which means that the number of bad cases doesn't depend on the location of this shape in the graph, rather than the number of shapes that exist in the graph. This observation helps us to bound the number of bad events and actually to prove that this construction induces a 4-color tree code as we wanted. We're finally ready to see our palette alternating tree code construction. So as stated before, our interactive coding scheme uses a palette alternating tree code that consists of a lot of layers with 2 colors and once in a while a layer with 4 colors. So keep that in mind and consider the trace function from the field F4 to the field F2 that defined as follows. Given an element X from the field F4, it returns x plus x squared. Now, there are two very important properties of this function. One is that given a uniform element from the field F4, it returns a uniform element from the field F2. And second is that this function is linear over the field F2. Now, a very natural way for constructing the palette alternating tree code using the construction that we saw in the previous slide is that for the two color layers, we just get the color that we got according to the previous construction and apply the trace function. And so with that idea, we could surprisingly prove that these trees actually exist. We are now ready to see our capacity approaching coding scheme. So recall that in our model, we're dealing with alternating protocols, meaning that at the odd rounds, Alice sends to Bob exactly 1 bit, and at the even rounds, Bob sends to Alice exactly 1 bit. Now here's a thought experiment. Imagine a model that together with the new bit that Alice sends to Bob, Bob receives all the messages that Alice sends him so far for free, meaning without costing the rate. Assume further that only epsilon fraction of this new kind of messages arriving incorrectly to Bob. Now a closer look made us realize that tree code is exactly the object that allowed the reduction between those two models. In order to do that, we use this lemma by Schulman, which states that if you have tree code with distance delta and a channel with epsilon fraction of adversarial errors, then there are at most 2 epsilon over delta fraction of incorrect messages in the new model. In the following slide, we are going to delve into more details of these ideas. Okay, so in this slide, we are going to take a closer look of how deterministic interactive coding schemes make use of tree codes. So basically, when Bob gets a message from Alice, he just can't know whether this message was corrupted or not. This machinery states that before Alice sends her bit to Bob, she encodes it using her tree code and then sends it across the channel. On the channel, the adversary may corrupt it, but then Bob will decode it using his tree code. Now recall the distance property of the tree code, which states that the relative Hamming distance between every 2 different paths is relatively large. And so as the conversation unfolds, either Alice or Bob will understand that something wrong has happened and that they should rewind the protocol back. This machinery allows the reduction that we saw in the previous slide. In the previous slide, we saw how tree codes came handy and how they helped us to recognize the corruption that happened across the channel. But of course, that this is not enough in order to construct the scheme that we wish for. Our scheme should have some kind of regret mechanism that allow Alice and Bob to drop some wrong parts of the conversation that happened so far. Now, since the scheme should have rate close to 1, we cannot afford that after every data bit that has been sent, either Alice or Bob will send an indication that everything is okay. So our scheme is divided into epochs, where each epoch consists of t data bits and 1 indication bit for every party, where the indication bit says whether Alice and Bob are happy with what they saw until now. If so, the conversation can continue from where it is. But if not, namely either Alice or Bob saw that a mistake has happened, they should rewind the conversation for 2 epochs back. And so it allows the scheme to regret. Together with the machinery of the tree codes that recognize that a mistake has happened, the conversation can end with the right result without adding too much overhead to the protocol. Okay, so now we get a better understanding of how we analyze our scheme. Now, recall the adversary can choose where he put up to epsilon fraction of the symbol for which he corrupts them over the channel. So in this example, we see that the devil emoji and the red line indicate whether the adversary corrupt the symbol that's sent across the channel. Now recall Schulman lemma that we saw some previous slides ago. which state that if every bit is encoded using a tree code with distance delta, and there are an epsilon fraction of errors, then there are at most 2 epsilon divided by delta fraction of incorrect messages. In this example, the incorrect messages are the letters which colored by red. Notice that 2 epsilon divided by delta is not that much bigger. And so there are not a lot of places for which Alice and Bob got an incorrect message. Now, recall that our scheme said that we use the rewind mechanism only if Alice and Bob indicate that something has gone wrong. Now, since we don't see there are a lot of bad messages, we can bound the number of times the rewind algorithm has been used. And so we can conclude that the protocol will terminate with not adding too much overhead to the original protocol. Now, using Schulman quantitative result, we could prove that the algorithm achieves rate of 1 minus the third square root of the entropy of epsilon, which is not what we wanted. So in order to achieve capacity, namely 1 minus the square root of entropy of epsilon, we had to prove some stronger lemma, which gives some structure about the incorrect messages locations according to the adversarial error locations. We'll see this in the next slide. Using Schulman's lemma, we had that there are at most 2 epsilon over delta fraction of incorrect messages. But as this result is only quantitative, it seems like the incorrect messages locations could be spread over the entire protocol. But this is not what really happens. Namely, in our paper, we were able to prove that if the adversary corrupts a message, there is a potential of influence on the consecutive rounds that decays over time. And so if the adversary wants to increase that potential, he has to corrupt some more messages. In this example, if epoch K is out of the scope of that potential, then all the messages that sent in epoch K are correct. And with that, we could give a tighter bound on the number of times the rewind process has happened. Using this idea, we show that our scheme doesn't add a lot of overhead to the original protocol and actually has rate of 1 minus the square root of the entropy of epsilon, which is what we wished for. In this talk, we devised a deterministic interactive coding scheme that achieves capacity that was based on a new notion we introduced named palette alternating tree codes. But as we saw earlier, those palette alternating tree codes constructed in a non-explicit way, meaning that our device scheme cannot be implemented in efficient amount of time. So one big open problem is to construct an explicit palette alternating tree code, namely giving an encoding and decoding functions, and by that showing the existence of the deterministic and explicit interactive coding scheme that achieves capacity, which is a very significant result. But it seems to be very hard to construct an explicit palette alternating tree code, as actually we don't know how to construct regular tree codes with constant number of colors. The truth is that as for rate consideration, the best tree code that we've got is by Cohen, Hopler, and Schulman, and uses polylogarithmic number of colors. Another notion that was introduced by Gelles and Sahai is potent tree code, which is actually a relaxation of tree codes and may seem be easier to construct. So another open problem is to explicitly construct them. Okay, so that was it for this talk. Thanks everyone for watching.